In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 5, Elastic Plastic Analysis of Bending, Part 9. So far we have talked about plastic hinges and collapse load, and we have used the method of virtual work to solve difficult or indeterminate problems. In here we are going to use the same idea again, but I'm going to introduce to you a new concept, and that's the velocity hodograph. What is the velocity hodograph? Now in this figure I have shown you the same problem that I solved at the beginning of the introduction of the virtual work, and that is a built-in beam like that, AB. At point C in the middle, the load P is applied, and we assume that A, B, and C become fully plastic when P reaches the collapse load and the beam collapses. Okay, and we said that this beam moves with the velocity omega, and this beam also, this member, we assume that AC and CB behave like members or links in a mechanism, and upon that, based on that assumption, we use the velocities and the movement of point C, virtual movement of point C, to derive this equation. Now this equation is the load P, the velocity W times L, omega times L, in fact, is the movement of the beam, per second. That gives us the rate of the work or rate of energy or power, P dot omega dot L. And we said that we have one MP in here, omega AC, and we got another one, omega BC, and we got two of these omegas for a point in the middle. Okay, and of course these omegas are equal. And MP also is equal because it's a fully developed plastic moment at points A, C, and B. Now in here I have drawn a very simple diagram. Point 0 means the velocity is 0. Okay, point small a is showing the velocity for this link. Okay, the angular velocity for this link, and I'm saying that this is the velocity for this link, for link AC, and I have shown it by this amount. Of course here I have taken the clockwise sign as positive. Okay, sometimes we take it as clockwise as positive, sometimes we take it as negative. As far as you mention which is positive and which is negative, it doesn't matter. So we have taken it as positive here, and OA is positive, equal to omega. We have this omega over here, so that's negative, and we have this OB showing the velocity for this link CB. Therefore, this is what we call a hodograph. In fact, is a graph of showing the velocities at different points in our geometry. At different points in our geometry, we have the velocity. For instance, CA is moving with omega, and CB is moving with omega in different directions. So we got from there to there, and also point 0 showing point B, and point A. Okay, so going from CB to CA, I mean moving from right to left, from right of C to the left of C, is like going from here to there. In fact, we get 2 omega. Omega in that direction, omega in that direction. So moving from there to there, we get 1 omega here and 1 omega here, so we get 2 omega like that. Okay, so we got 1 omega for AC, 1 omega for BC, and 2 omega for this point. But moving from here to there, we get 2 omega. Okay, from here to there. Okay, then let's see, and that was the collapse load that we obtained. Therefore, there is a jump of velocity from minus omega to plus omega, as I said. So we have, in fact, 2 omega is the velocity discontinuity. In fact, that is the velocity discontinuity because the velocity is constant here, but it suddenly changes to plus omega, from plus omega to minus omega, moving from left to right to left, from minus omega to plus omega. So a magnitude of 2 omega, the velocity changes. Now, in this page, I am considering a stubby cantilever. What is an stubby cantilever? A stubby cantilever is a cantilever like this, which has a length and depths which are comparable. Okay, that H and L are comparable to each other. That means their dimensions is near. Okay, if we had a very long cantilever, then that we wouldn't call it a stubby. Stubby is like this. Okay, is a fat cantilever. Stubby is a fat cantilever. So this is our stubby cantilever. Also, I have drawn some lines in here. Okay, I have drawn this blue line and this red line, and this R is the radius of this blue arc. Okay, R, and 2, 5, 0, O is the center of this blue arc. Okay, now this shear force SH is acting on the beam, and this blue arc that I have drawn, I have assumed that this is where the complete plastic bending occurs. Okay, complete plastic bending moment occurs at this point. Obviously, it is at this point because SH times L is the maximum bending moment. So maximum bending moment is at the root of this stubby cantilever here, where it is connected to the wall. That's why it's built in. And so we assume that this portion, like that, this portion is becomes plastic here. All of this becomes plastic. So it revolves around this arc. Okay, that's our assumption. So our plastic hinge, in fact, here is an arc. It's not a point. Okay, why we have taken it as an arc? Because this is a very, very fat beam. You know, H is very big relative to L. If H was very small like that, then we wouldn't take it as an arc. We would have taken it as a point. Let me just show you here. For instance, supposing we have a line, a beam like that. You know, it's long, and the depth, that's the depth. Depth is small. Then we would take a point here as the plastic hinge. But because this is a very, it has a very big H value, then we take an area as the plastic area, not a point, as a plastic area. So that's why we have taken it as an arc. Okay, so let's see, rate of work done per unit width. We are saying that how much is the work done. Let me just erase all of this. Sorry. See, rate of work done per unit width. Per unit width, width is the dimension perpendicular to the screen. Okay, so we take it as unit. So SH, which is the force times the area. Area is that unit width times this area. What is this area? Is L plus R cos phi naught times omega. Okay, because that's the rate of work done. What is work done? Work done is the force times distance moved. But here we have force times distance moved per second. So that's the distance moved per second. L plus R cos phi, because it's moving about this point, you know. So that is the distance. That is the distance. So that R cos phi naught, because that's 2 phi naught and that's phi naught. So R cos phi naught is this line. So that is the point, that is the line, and times omega, because omega is on this arc. As I said, it revolves around this arc. So that line times omega becomes what? The distance which is revolving around this. Okay, so that's the distance times force gives us the work per second, gives us the power or rate of work. Now on the other hand, now this is the external work. That's the external work, the virtual work, because it's not really moving. We are just assuming that it is moving. So that's why we call it virtual. It is not real. It's virtual. We are assuming. We are imagining. You know, that's the imaginary work. So what is the complete plastic shear force? Complete plastic shear force happens on this arc. Okay, so R times 2 phi 0 or naught is the length of this arc, okay, or the length of that arc, doesn't matter. So the plastic shear force happens in here, and because it's complete plastic shear force, therefore we multiply it by K, which is the shear yield shear stress. Okay, yield shear stress on here is K. So yield shear stress times this line and times the unit width perpendicular to the screen 1. So that becomes the plastic shear force. And here we get the rate of plastic work done in the circular arc. Okay, work done in the circular arc. That is the force times the distance, which is, so that's the force R times 2 phi naught times K times R omega. R omega is this distance. Okay, R times omega is this distance per second, because omega is movement on this arc, and R times omega gives us the velocity. Okay, the velocity on this arc, the velocity times force gives us the power, because velocity is distance moved per second, as it was in here. Okay, the same thing. So we equate these two powers, that one the virtual power and this is the internal power. So if we equate them together and simplify them, okay, that is that S of course is the unit shear force, and SH is the shear force per width, unit width. Okay, that's how we have written it here. So in here we have shown s over k is equal to 2r squared phi naught h L plus r cos phi naught in here, and h also is this distance, that distance. So that distance is r sine phi naught, and that's 2 times 2. So substituting for h in here, we get s over k is equal to this, okay, phi naught divided by half sine 2 phi naught plus L over h times 1 minus cos 2 phi naught. Okay, so that's how we obtain the collapse load for this stubby cantilever. I have a couple of things in here that are unknown. For instance, something like phi naught, and of course L and H, we can, if we put numbers for them, then we are okay. So we have to determine phi naught. So I differentiate relative to phi naught and put it equal to 0 to see what value I obtain. That is the value I obtain if I partial differentiation of s over k to partial phi naught, put it equal to 0, this one, then do some simplification, I get this relationship in terms of phi naught, and that is L over h times 2. So if I substitute this for phi naught here, I can substitute for L over h, okay, or I can substitute for phi naught in terms of L over h. Okay, it's a bit difficult to solve this, but if you have numbers here, for instance, if you have L is for instance 20 centimeter and h is 15 centimeter, then you get a number here and you can obtain phi naught, and you put phi naught in here and you get s, okay, because k is known. K is the yield shear stress. So another method for computing the collapse load using fully plastic moment for a rectangular section, supposing this is a rectangular section, then we had obtained before MP for rectangular section. MP is equal to BH squared y over 4, and if we put y equal to 2k, we get MP is equal to this, okay. SHBL is the that shear force per unit width, that B is width times L gives the bending moment, and that is equal to BH square 2k over 4. So in here S over k, like here, we get 1 over 2, 1 over L over h. Now because we don't want to confuse this S over k with that S over k, so I put it here S prime over k, so that I know I obtain this from this relationship, not the collapse load method. Okay. Now what is this? This is the hodograph for this diagram. Now I have put many points here, point 1 there, point 2 there, point 3, point 4, point 5. Okay, obviously this beam, when it fails, it only revolves around here, it does not deform in any other way. Therefore point 1, 2, 3, 4, 5 remain the same relative to each other, but they have their absolute velocities changes. Now I have shown point O in here like that, so this is perpendicular to that, and this is perpendicular to that, or you could say that this is parallel to that and this is parallel to that. Now that's this 1, 2, 3 is the velocity of 1, 2, 3. If you can see here, for instance, if I let me just draw this line, okay, try to use my pen here and draw this line. Now if I carefully draw this line to point 2 here, okay, what is this? This is the velocity at point 2. So what is the velocity at point 2 here? That is the velocity at point 2. Okay, tangent in here is this, see? And this O1 also is the tangent in here. Okay, and the other one is tangent in here. So this one and that one are these tangents, okay? Because the velocity on this arc at any point is this radius times omega, which is the velocity and is perpendicular to r, or tangent to the arc. So all these points 1, 2, 3, or any other points between them, we get the velocity. So what is the velocity of point 4? Obviously 4 remains the same relative to 1. So if we put a line like that, 4 and 1 remain the same, 3 and 4 also, 3 and 5 also remain the same. Okay, so that's how we obtain the hodograph. That's the hodograph. Okay, the velocity at any point is known. This point, or any other point in here, we know the velocity using this hodograph. Now we want to compare the value we obtained for S over K using collapse load method and the value of S over K using the ordinary plastic moment method, which we obtained at the beginning of this chapter. So I'm going to compare S prime over K with S over K, and that's how we compare it. If we change L over H, the dimension of the beam, as you can see, it's 0.42, 0.875. It becomes almost equal. So L over H up to here is this one, is a stubby cantilever, okay, fat cantilever. But when it becomes 3.08, 12.9, or very big, it is not anymore a stubby cantilever, and it's a slender cantilever, okay, very thin, the height relative to length. So in here you can see how these differ. For instance, phi naught 30 for this, 45, 60, 65, almost 67. But look at S over K. A lot of difference for the stubby cantilever. See? Very different. In fact, this here is showing that using the collapse load, you get a smaller value for S. But here you get a larger value for S. Therefore, this is not correct for stubby cantilevers. The collapse load gives you the better answer. Okay, here you can see the difference. And also here, it changes again. Okay, because it's not anymore a stubby cantilever. So you get with this one you get lower answers. Okay, lower answers, which is the correct one. Because if you use this answer for the collapse load, you get higher loads, but here you get lower loads. Here much lower, and obviously for infinity you get almost the same, because it becomes 0. We should maybe write for infinity here some big numbers. Okay, some big numbers. Anyway, that gives us the idea where we should use the collapse load for the cantilever beam. Okay, otherwise we could use the ordinary plastic method. Okay, but for stubby cantilevers we use the collapse load. This example is very intriguing for me and interesting. I'm very interested in this example because it reminds me of the design of gear teeth, for spare gears. If you remember, this is our spare gear, okay, the tooth of a spare gear, and if you remember, we said that the load is applying at the tip of the tooth, and we have the radial load and tangential load, and in order to get the bending moment relationships for the tooth design, we compared it to a cantilever beam. In fact, Lewis did this, Lewis method. Lewis compared it to a cantilever beam, and using the cantilever geometry, Lewis obtained a relationship for the bending moment. Okay, it would be interesting, I think, if we use the same relationship Lewis used, but use this one, this relationship for the collapse load, because as you can see, a tooth also is a stubby cantilever. It's not a slender, it's a stubby, it's not like that. In fact, here the width is very, or the H is very big, and relative to L. Yeah, so it's not like that, it's more like that. So it would be very intriguing to calculate the bending moment using this and compare it to Lewis method.